Okay, so in the previous video, we talked about carbocation rearrangements and one particular type of carbocation rearrangement. In that type of rearrangement, we refer to it as a 1,2 hydride shift, basically saying the hydrogen on a molecule can potentially move by one position if it actually increases the stability of the intermediate carbocation. So one thing to point out is that if you think back to Markovnikov's rule, Markovnikov's rule was a very quick and simple and dirty way of you to try to predict major versus minor product for an alkene reacting with a hydrogen halide. It's a very important thing to note here that if you tried to invoke the Markovnikov rule, then you're actually going to get an incorrect answer, because Markovnikov would kind of predict the hydrogen should go on position 1 and that the bromine would go on position 2. Now, Mark would actually, according to the mechanism, you could prove to yourself that the purple would go where the Markovnikov's rule would predict, but the bromine actually ends up going on carbon 3 instead of carbon 2. So, and again, this is carbon 3. So one thing to be careful about is that once you get into more complicated alkene scenarios, you have to be careful about not just blindly following Markovnikov's rule, because it can lead you to incorrect answers. Another thing that I wanted to make sure you're absolutely clear about is that this numbering scheme that I'm utilizing has absolutely nothing to do with this 1,2 designation. So again, the 1,2 is just basically saying start and stop for the hydrogen. These numberings that I'm using are just kind of completely arbitrary, just so I could talk to you about positions verbally. I could have just as easily, called this guy Bob and this guy Bill and this hydrogen Happy Face. This is just so I can talk to you and you can kind of see my thought process. So don't get too hung up on this numbering scheme. All right, so the next topic that we need to talk about is, well, we said that hydrogens can do this shift by one position. And so then a common question is then, well, what about the hydrogens moving by 3? And it actually turns out that hydrogens don't do these 1,3 hydride shifts. Let me give you an example of a situation where you wouldn't get these kind of 1,2 hydride shifts. So I'm going to draw the first 2 arrows, redraw the molecule, and we're going to choose which carbon should get the positive charge, and again, either carbon 1 or carbon 2. And at this point, after doing a whole bunch of problems, it should be obvious that 2 is going to give you a secondary carbocation, and 1 is going to give you a primary. So if you had to choose, the first choice that you should make is putting that positive on carbon 2. So now we've got a secondary carbocation. So this is a secondary. If we were to do a 1,3 hydride shifts, which again we're saying these guys don't really occur, what you would try to do, and you would be doing this incorrectly, is you would be trying to say if this is the end position, or the third position as the end, and this would be the second, that means this would be the first position where it starts. This means that the hydrogen could kind of do this kind of movement where it skips this carbon 2. And this would give you a product that kind of looks like this. So it's very tempting to, even though we say that 1,3 hydride shifts don't occur, it's very tempting to try to draw this molecule like this, because you can go from a secondary to a tertiary. And we said that molecules, they're very opportunistic. Anything they can do to kind of stabilize their energy is they're going to try to take advantage of. Unfortunately, the 1,3 hydride shift, even though if we could do it, it would stabilize the carbocation, it's not really in the cards. It's not really an ability that the molecule could have. Try to remember that you cannot do this kind of hydride shift. So 1,3s don't work. So then a very common thing after that is for students to say, well, okay, so I can't do a hydride shift, so let me redraw the molecule, and I'm going to try to actually break this up into discrete steps. So this is the same thing as I drew before. We've got our secondary, and so then, well, what's keeping me from going from this molecule and doing a 1,2 shift? So we said that 1,2 hydride shifts were very possible. These are allowed according to our rules, and we could get this molecule right here, so something like this. And then after that, we have another hydrogen. We could do another 1,2 hydride shifts. This would be your 1 position, 2 position, and this is your 1 position, and this is your 2 position. So we're really just doing 2, discrete hydride shifts instead of one big 1,3 hydride shift. And so if you redrew the molecule, you'd find, well, okay, it looks like we're getting to the same spot. So really, why can't I actually get to this molecule? It turns out that in order for the molecule to do 1,2 hydride shifts, it's actually kind of a short-sighted type of perspective on the world. The molecules have a very short-sighted perspective. So it is possible for these two hydride shifts to happen separately and discretely. But the big roadblock here is that we have secondary carbocation here, and after we do this shift, we have another secondary carbocation here. So going from A, we then make B, and then if we could go from B to C, that would be very stabilizing because we go from a secondary to a tertiary. The only problem is that going from A to B, there's no real immediate incentive for the molecule to do this shift because there's no a stabilizing effect that's happening. So going from a secondary to a secondary, that's not very helpful. And because the molecule is very short-sighted, it doesn't realize that, oh, if I just do this, one step, I can benefit another step afterwards. So because the molecule doesn't realize that, it's actually not going to be able to do these two discrete hydride shifts. So if you actually had to try to predict the major product of this type of reaction. So if we were to complete the mechanism, in this case, we'd have the Br minus coming in. So at the end of the day, this molecule is going to be your major product. And molecule C is going to be 0% of the possible products that you can form. And then, of those two, you could then say, well, maybe there's another bromination product at this first position, and I'm sure there will be a little bit of that. So in this case, we could say major minor, but the important part is to be able to predict that this molecule is going to be the major, and it's not really going to be able to benefit from any kind of hydride shift.